Alright, let's have a look at the limit chord process and average rate of change. Now, by the end of the lesson, you should be able to define the chord of a function and examine how the limiting chord process can be useful in approximating the gradient of a function at a point. You should be able to define the average rate of change of a function using the difference quotient, and finally calculate the average rate of change of a function. Now, I introduced in the last lesson, when we look at the rate of change, we know that it is a gradient, and to derive the gradient of a curve at a point, let's say the curve of x, fx equals x squared, at a point x equals to 2, what I did was to draw a tangent really close to that point. And then I work out the gradient. Basically find 2 points, this point here and this point here, and work out the gradient. M equals to y2 minus y1 over x2 minus x1. Alright? This time we're going to take the step, take this a little bit further. Let's construct a chord joining the 2 points on the function fx equals x squared. Let's call it point A. Now I'm going to define the gradient between the 2 points A and B on the curve is actually the average rate of change. So make sure that you know the definition of average rate of change. And you can therefore work out m equals to y2 minus y1 over x2 minus x1 if I know A is A and FA and B is B and FB, and therefore we can work out m is actually FB minus FA divided by B minus A, which is actually the difference quotient. Now we can actually put this in the table. Point A, now we know that A is minus 1, x is minus 1, so therefore y is actually 1, correct? Yeah, so you know that, let me write that properly, minus 1 and 1. So therefore we could work out the gradient of chord AB, which is the average rate of change between A and B, is 1, which is 4 minus 1 divided by 2 minus 1, which is 3 over 3, equals to 1. Right? Now, the aim is move A close to B, as close as possible, so that the chord actually becomes a tangent. Let's have a look. This time, let's move A from minus 1 down to 0. Alright, you can see that the gradient is actually closer to tangent now. So this time, working out point A is 0, 0, and we can work out the gradient as 2. Let's keep going. Moving A to 1. Alright, from minus 1 now to 0 to 1. You know that therefore A is 1, 1, and now the gradient of the chord AB is 3. You can see that AB is getting closer to the tangent. Alright, let's move A even closer. This time I'm going to use 1.5. And therefore, you've got x squared of 1.5 is 2.25. You can work out the average rate of change between AB, or the gradient of chord AB, is 3.5. Keep going. This time a little bit closer, 1.8. And we can work out f excuse me, f of 1.8 is 3.24, and the gradient is 3.8. Next, move even a little bit closer, 1.95, and you can work out the gradient of chord AB is 4. And let's go up to 1.99. Again, the gradient of chord AB is 4. So now that you've got that, what we can say that AB now approximate the tangent of at point B, or we should say the limit of the gradient of AB as A approaches B appears to be 4. So the gradient at B is actually 4. Alright? Now, the limiting chord process. What you need to do is choose a fixed point B for which you want to find the gradient of the curve at that point. Then you choose a sequence of points A, N that move closer and closer and closer to the fixed point B. Then calculate the gradients of each chord AB. Then you state the limit of the gradient of chord AB as A gets closer to B such that the chord AB becomes a tangent. Alright? I would like you to pause the video for a while. Oh, before that, we can actually think about approaching any point P of fx using the chord from either direction and still obtain the gradient at that point. Let me explain what I mean. So what I showed you just now is when we are looking at point B. We started at from point A1 here. Then we go A2, A3. We are moving from the left until A whatever. Could be AN, which is really close to B. Whereas we could actually start off with another point. If this is point B, we move from here, limiting the gradient from above. We move down until we move as close to B as possible. So it really doesn't matter we move from the left or from the right. Alright? Now, I would like you to try this example. Alright, using the limiting chord process, calculate the gradient of the curve of fx equals to minus 3x squared at the point x equals to 1. Now, I've given you the first one. The point A is here. This is the point B. 1 minus 3. Alright? So, what happened is, if I work out 0.5 here, x is 0.5, you should be able to work out this is f of 0.5 equals to minus 3 times 0.5 to the power of 3. Alright, so you keep going until you can find the gradient of chord AB and it's really close to B, and then you can work out the gradient. Let's try it. So pause the video for a while and you might do it yourself. Alright, try this. Now here, if I started from A here and point B here, if I draw a straight line, you can see that the average rate of change or the gradient of chord AB is minus 3. Alright, keep going. Minus 5, minus 3 times 0.5, not minus 5, 0.5 to the power of 3 is actually minus 0.375. You can work out the gradient. Keep going until you get to 0.999. You can see that the gradient is minus 8.99. Or we can actually set the limit of the gradient of AB as A approaches B appears to be 9. Alright, so I would like you to practice a few of these. There should be enough exercises in Saddler or Club for you to do. So hopefully you should understand how you could do the limiting chord process and you could approximate the gradient. Alright, I'm going to stop here